So this section is about alternating series, and the sort of baseline thing to remember is alternating harmonic series converges conditionally only. So converges only conditionally. Okay, and so that's the main point from this discussion. But let's talk about that in detail. So first of all, remember why the regular harmonic series diverges. There's two different ways you can show that quite easily. One is just add them up in bundles that are 1/2 or greater, and there's an infinite number of those. Or you can integrate. Either of those work just fine. Okay, so now let's split up the alternating harmonic series, into the positive pieces, which is 1, a third, a fifth, a seventh, all the ones with an odd number in the denominator. And then all the ones with the even numbers in the denominator will be over here, okay, and that'll be series B. So series B, let's look at that. That is like the regular harmonic series, but it's all divided by 2. So it's just infinity over 2, which is infinity, right? Okay. And then we can use the comparison test on series B, and, well, in each case you have a 1-to-1 correspondence. The terms are only bigger as they're paired off like that. So, you know, C is clearly less than A and more than B, but they're both infinity, so they're all infinity, right? So, you know, that's all it can be. So now what the question is, A, over here, A is C minus B, right? So you have infinity minus infinity. So let's talk about that a little bit. If you have two piles of infinity, it's kind of like having hot and cold tap. You know, you can make that temperature go anywhere you want by adjusting the speed at which the hot water comes out and the speed at which the cold water comes out, and you just keep tweaking it until you get the temperature you want. So what you can do is you can line up the line up the B's and line up the C's and say, okay, I'm going to take two B's and then two C's, and then all these guys, the B's are all negative, right? So they're all actually negative, so that's negative infinity, right? So I could take like two C's and a B, two C's and a B, three C's, two B's. But the point is, there's a C line and there's a B line, and everybody in each line is eventually going to get wrapped up into the sum, right? So since everybody's got an appointment to get added in, then it should be fine, right? But it's not. So when you have two infinities, you really have enough freedom to just converge anywhere you like. That doesn't happen if you have a pile like over here, instead of infinity, if this is +7, and over here this is -3, then it does not matter what order you take the pieces in, as long as you include everybody eventually, then you're going to have to converge to 4 no matter what you do, okay? But when you have infinities, you have funny things that can happen. Now, what if instead we agree to take a C minus a B, then, you know, another C minus another B, and you just zigzag, zigzag, zigzag in exactly the order that the index tells you to go. Now you have imposed an ordering, and in that case, then you can actually do something with this. Okay, so what's going to happen is, let's say in each bundle, you're going to have in each pair, we're going to call this guy like 3, in this case n, and then this would be n plus 1. Now what happens? Now I'm just going to let n be only odd numbers, but look at the algebra. This whole thing works out and you get this mess. Now remember, I'm only adding up the odd ends, but my integral is going to add up everybody, not just the odds, the evens, everybody. It doesn't matter, right? Because we're just trying to find out if this thing converges. So we don't care about the value, we just care about whether it's finite or not. So multiplying by 2 or adding in all the in-between terms, it doesn't matter. It doesn't matter. So question, does this converge? And this will converge, okay, because this is its dominant term in the denominator is 4x squared, so it will converge it's something I don't want to integrate. I don't think I can integrate it, but it doesn't matter. I just know that it's finite. Okay, so just to summarize, harmonic series diverges. This guy is half of the harmonic series. This is harmonic series minus half of the harmonic series, so it's like the other half of the harmonic series, but it's not, we're talking about half of infinity, right? But when you go infinity minus infinity, you just get messes. And so if you want any kind of convergence, you have to agree on some kind of convergence, some kind of ordering. Otherwise, you're not going to get a guaranteed convergence. Okay, related concept, you guys had a homework question like this, something like this. We had some function, I'm having trouble controlling this, sorry about that. Okay, so we had, from minus k to k or minus alpha to alpha, we had some kind of, here we have, an even function, even because it's rotationally symmetric, 180 degrees, okay? Right. And so if you go from minus a or minus alpha to alpha, you're going to get an integral of 0, right? So this structure that you saw in this problem online on your homework, okay, this was specifically rigged that these two limits were moving outwards at exactly the same rate. And so this is kind of related to the idea of conditional convergence, right? Because you're controlling something very, very specifically in order to make two infinities go, to exactly where you want them to go. In this case, 0, all right? But if you just wrote this without putting all those special rules in, and you just said, okay, let's go minus infinity to infinity, then that's not considered a good integral, because we've got this, we've got this infinity and this minus infinity. We've got a lot of messes going on. We're not going to permit that. But this question over here is asking something very, very different. So if this were good, if this were a good function and good limits, everything worked out, then the other guy, then this too is good. But that's not what happened, okay? Instead, we got a situation where only the carefully defined speeds of the two integrals going out at exactly the same time, that was okay. But we were very, very careful. Okay, hopefully that makes sense. You guys seem to understand that in class, so hopefully it makes sense. Okay, alternating series test. So, in a later discussion, we'll talk about how this works in 2 dimensions or 3 dimensions, but let's just talk now about alternating series test. If you have here some kind of mechanism for the sign to alternate, and we'll have various mechanisms that will cause an alternating sign, and then we have Bn, and we're going to say Bn is strictly greater than 0. That's the only point of this, is to say this tells us that this sign is alternating. It would do us no good if Bn didn't have to be positive. We have no idea what the sign is, right? And then the alternating piece here would be meaningless because it would give us no information. Okay, so as long as the Bn's themselves are positive, and then all the sign is determined over here, then what we're saying is if these Bn's are decreasing down to 0, then we will have conditional convergence. And it's really easy to figure out why. It's like a kid on a swing. You push the kid and you walk away. Okay, not too far. You push the kid and the kid goes forward, like the swing goes forward, then it goes back not as far. Then it goes forward and back not as far. And the kid eventually settles down because each swing, each forward or backward swing is not going to be as far as the last one. Right? So you have to be always dancing over your limit, and eventually you'll reach your limit. Okay, here's a bad example. This is not something that has conditional convergence, And why does it fail? It's because, first of all, we don't look at that. We just want to see why this is failing. I mean, that part was okay, so we ignore that. So what's happening? Is it decreasing? Well, if you write out all the algebra, this guy actually is decreasing. But the problem is, it's decreasing to 3/4. You see the 3 and the quarter here. So it's actually, it's not good. You're not allowed to decrease to 3/4 because then you're just going plus 3/4 minus 3/4 plus 3/4 minus 3/4. And, that's not really going to do anybody any good. That's not going to converge. Okay, so what about this next question? What about this next one? Does this guy converge? Well, this kind of looks like 1 over n, right? So this is just like alternating harmonic series. It's just in disguise. So yeah, it's fine. What about error bounds? Okay, so we have all this crazy notation. What's it mean? This R means remainder. S is the actual sum. And then this is the nth partial sum. Okay, so the remainder is obviously the actual sum minus the nth partial sum. That you don't need a definition to tell you that. And it has to be less than or equal to the next term that's missing. So this is all intuitive, and it just looks weird sitting there in a formula. How many terms are needed to guarantee 3 decimal places? Okay, so what you do is you just go and say, so this is a good example of a question that I could ask you that doesn't require a computer, because you could just figure this out. You could just say, well, you want to make sure, it depends what you mean by 3 decimal places. You want exactly 3 decimal places, then the next piece should be actually, error, this is greater than error, something like that. So you probably want maybe more than 1,000. Maybe you want 10, 100,000. Maybe you want 200,000 or something like that. I'm sorry, 2,000. So all you have to do is keep hiking up n until n factorial is greater than 2,000, and then you can say, fine, we're good. You're like, well, that's a lot of terms. Well, it's not actually, because by the time you get to 7 factorial, you're way past where you need to be. And so if you just take 7 terms, you're fine. I mean, you take 7 terms, you're way safe. Okay, so now what? Some questions that might help you on the homework. I just wanted to mention that this piece, sine of n plus a half pi, this is just another mechanism for doing +1, -1 toggling. Okay, so don't be taken by surprise when you see that. And square root of n strictly increases, so 1 plus square root of n strictly increases. So this is going to have to converge conditionally. Does e to the minus n win over n? Well, yes it does. And so we can use L'Hopital's rule. This only tells us that these terms are decreasing down to 0, so it only gives us conditional convergence. However, I'm not going to show you right here, but I showed you in class. We took a long time. We took a long tangent trying to show that this converges absolutely, because in the upcoming chapters we will have more powerful tools and we can do this very quickly. We can actually use a comparison test or an integral test and other things we can do to prove that it converges absolutely, which means we don't actually care about this -1 sign here. The toggling -1 doesn't matter. So if you say this converges conditionally, it's like, not really. I mean, it does, yes, it does, but you're misleading someone if you say it converges conditionally, because it actually converges absolutely. And this -1 to the end is, you're obviously going to converge somewhere different because of the toggling sign, but the toggling sign is not necessary in order to make that converge. Okay, another thing you should keep track of is arctan does have an asymptote, and it's not at 1. I don't know, a lot of people seem to think it's 1. It's not right. It's, I think because people are thinking when tangent is 1, that's where that's converging to, but it's the angle whose tangent is 1, right? So Anyway, here we go. Next example. Let's say we have a toggling sign, and then we have n over, what's this mess? Square root of n cubed plus 2. Just in your mind's eye, that plus 2, think about it. As you're going out to n is 100, 1,000, a million, you're taking n and cubing it and then taking the square root. You are not going to see that 2. That 2 is just going to disappear. You should intuitively understand that by just imagining numbers that are that big. It should be like, oh yeah, obviously the 2 is going to wash away. And so this is like 1 over square root of n. So it's not good for absolute convergence because you can just compare to the alternating, compare to the harmonic series, and it's obviously not going to converge absolutely. But it will converge conditionally, so, you know, that's what we're all about. And, okay, this little thing I want to just ignore. You don't have to read this. Scratch, sorry. I mean, it's true, but I don't want to talk about it. Okay, I just wanted to kind of point out, if you have a pile of plus infinity and minus infinity, but it goes somewhere, you got conditional convergence. Okay, and I'm just abbreviating that CC. If you have a pile which is some positive constant and a different pile of negative constants and you're adding them together, there's only one possible place where those guys can converge because both the negatives and the positives were finite, right? So here's the deal. Think about it. If you have, you know, checks and bills coming into your house and they have to balance out to how much money you have, right? You can add up your checks and bills in any order. Like you can deposit your checks and pay your bills in any order you want. And at the end of the month, guess what? Your bank account is going to be exactly the same. But if you have conditional convergence, that doesn't work because what it means is you have an infinite number of bills coming in and an infinite number of checks coming in. And as long as you have a scheduled payment for each bill and each check, then you can get away with that. So you just say, okay, well, I'll just deposit 3 checks and then pay a bill, and deposit 3 checks and pay a bill. And, well, it's kind of weird because obviously you're not going to really finish that process because, you know, we're talking about infinities, but you're going to converge to something. And you may say, well, that's cheating because you're depositing more things than you're paying out. And you're like, yeah, sure, but that's what conditional convergence means. All right? And then divergence. Divergence is like you don't have 2 infinities. You have a positive infinity and maybe a teeny bit of negatives. Or you have a huge negative infinity and a teeny bit of positives. But no ordering can control for the fact that you have an unbalanced infinity. You have either a positive or a negative infinity and not the other. So then the ordering doesn't matter again. So like if it's absolute convergence, the ordering doesn't matter. And if it's divergent, the ordering doesn't matter. The only time your ordering actually matters is when you have 2 infinities that are fighting with each other, and then you get to control where it goes. Okay?